So I hope we'll have nice time in the next 3 weeks. Okay, so before I ask Professor Jamis to inaugurate the program, I want to say just a few words to you. Say, almost 12 years back, in the year 2000, the Clay Math Institute formed a very high-level committee to identify the open problems which are very important to the mathematical community and which the mathematical community should jointly work on in the new millennium. And the committee came up with, say, 7. Yeah, so the committee recommended 7 open problems, and the Clay Institute declared $1 million prize problem for $1 million prize problem for each of these open problems if you can solve or disprove it. And you know that one of these problems is already solved by Perelman in the year 2002-2003. Among the other 6 open problems, one is Navier-Stokes equation, which is considered as the most fundamental equation of the fluid models. So if you look back in the history of the development of the Navier-Stokes equation, you will see that people from Europe, UK, US, as well as from Japan have considerably contributed in the subject, but not that much of contribution has come from India. I don't know the reason for that, but some of us felt that since this is the National Mathematical Year in India, since we are celebrating the Ramanujan's 125th birthday, so we thought of doing some kind of winter school which will at least promote some research on this subject in India. So not only to Navier-Stokes, but deterministic and stochastic Navier-Stokes, as well as the control problems related to the fluid flow problems. So we talked to ICTS, and they happily agreed to support us. And so I hope that with these 3 weeks rigorous workshop, at least we can initiate some research in India on the subject. And there are only a very few people who are working in the topic currently in India. I hope that when they come here, they will share their experience, and probably we can have a forum on 14th, and there you can discuss how to promote this subject more in India. So I will now ask Professor Jamis to officially inaugurate the program, and then we'll have a high tea, and then we'll start our lectures. So Professor Jamis.
Well, friends, I'm glad that you're all here. A warm welcome to you. The Institute of Science Education and Research in Thiruvananthapuram started 4 years ago, and we are glad that International Center for Theoretical Sciences have agreed to sponsor and conduct this meeting along with us. For reasons best known to them, when ICTS started, I was asked to be a member of this team. I'm not a mathematician. I could drop names of mathematicians, famous ones, because there's an advantage of being a graduate student at Princeton. You move with people who are big shots, even if you are not in mathematics. So I could drop names of Hefferman and Ed Witten and Manjul Bhargava and so on without knowing what they do, really. So I would like to mention a few things about ICER. Some of you are aware of what ICER stands for, but there are others who do not know. When the government of India wanted to encourage higher education and research in the last 10 years, it started by encouraging engineering education by starting 8 IITs, management education by starting more IIMs. And when it came to science, they felt that we should have a few Indian institutes of science, and the result is 5 Indian Institute of Science Education and Research. The professors of Indian Institute of Science did not want that name to be used, and so there is this 2 words added, so they are different from Indian Institute of Science. We have the mandate of making the best institute for research and teaching in science subjects, mathematics, physics, chemistry, biology, and the like. And we have tried hard to get good faculty members, and I must say that it's the most difficult to get good faculty in mathematics. It is somewhat surprising, but India is famous for mathematics, but we have found that to get quality faculty in mathematics has been more difficult than in other subjects. We hope that there will be more of this spirit coming up, where we have input for the 5-year master's program after +2 with people specializing in mathematics, and PhD program in mathematics. And a lot of push has to come in from the mathematics fraternity of the country. It's not possible for us always to look outside and get. In this context, I also would like to say that ISER would like to support mathematics, whether it is a summer school, whether it is a winter school, workshops, whatever that is there. We are always ready to provide the facilities and the forum to run this. I'm glad that several of you are here from across the country and across the world for this winter school on stochastic analysis and control of fluid flow. I'm also glad to note that several busy people have agreed to be resource persons here. Professor Adimurthy, Professor Minal Ghosh, Nandakumaran, Rudiger, Shaiju, Sridharan, Suresh, a whole lot of others as the programs go by, and do not waste even a minute of time available, not only for cultural aspects, but for intensely interacting with people in the institute, even those who are not in mathematics, so that people get a feeling. Our undergraduates have largely gone, which was a little unfortunate, but the senior master students, I hope, will be available. What I would request also is that when you go back from this workshop, take a few memories of this place where attempt is being made to start a new institution from scratch. 4 years ago we didn't exist, and now we have a good beginning. Right? When you take this across to your own institutions, talk about ISER as a possible place where one could work in mathematics, any branch of it, and generate more manpower of the same kind. With these words, I inaugurate this winter school and wish you all the very best time discussing mathematics in these specialized areas. Thank you.
So we'll have some tea and then we'll come back around 9:45 for the next lecture, for the first lecture.
Any inconvenience that you have, should be brought immediately to the attention of Dr. Manda and other members of the faculty, so that there is a reason to be with the inconvenience. We'll try our best to make it right.
Basics of PDEs for people who are not so much, it's like a background building.
So, I really don't know it is a mixed audience, and some of them it seems know too much, some people don't know much. So I don't know what to do. To make it uniform, I'll start from the scratch, and if you feel that what I'm doing is very elementary, please tell me so that I can shift to the advanced topics. Okay. So the plan of the Settler, yes? Okay. I think I speak quite loudly. Let us.
No, but actually we are doing the recording of the.
Okay. Is okay? All are broken. It's like all the chalks are broken. Let me write down the contents of my course. What I am planning to cover in this one is the following thing. First is basics in LP spaces. To start with the sublow space. Here I am planning to cover embedding theorem. Secondly, density theorems, which should have come first. Density theorems and embedding theorems. Okay. Then compactness theorem, relic condensate. Theorems. Fourth, okay. Next is fourth, Fourier transforms, forms, and L2 sublow spaces. Fifth one, 1, 2, 3. Fifth one is elliptic boundary electrolysis. Here, trying to do weak formulation. Flax-Milgram lemma. Regularity results. So these are the main topics I am planning to cover. It is too much for 5 lectures. I will try to give as much information as possible and give proofs again as much. Otherwise, things are in my notes, and of course, it is already contained in a very good book by Evans. Okay, you can look into that. Okay, let me recall. Let me start with the LP spaces. So let us. I need the a basic. I need the notation. Let us start with some notations and definitions. Okay. So standard Rn denotes the Euclidean space. Xn, so that xi belongs to R. And inner product x dot y, I denote by xi by I, mod x to the power of half. Okay, just the notations. And omega normally denoted a bounded domain, but here it is a domain, open domain in Rn domain. That is a open bounded set. Oh, sorry, open connected set. D omega denotes the boundary of omega. So associated with this, I have some spaces. Let me start with some spaces. So k is an integer greater than or equal to 0, be any integer, and defined Ck of omega all functions f from omega to r, which are f is k times continuously differentiable function. And ck of 0 of omega, all functions f belongs to ck of omega, so that you know what is the support of a function. Support of f is compact in omega, contained in omega. Then corresponding to the k can be also equal to infinity. If k is infinity, it is infinitely differential functions. Infinitely differential functions with support contained in omega. So these are the basic notations I am going to use. Okay, let me recall the LP spaces. Now I will call this LP spaces. L1 log of omega. I call this L1 space first. I will call this P. So these are all measured functions f from omega to r or c. C is a complex number. So f is measurable. And for every compact set k contained in omega, k compact, integral over k mod f dx is finite. This is called locally integral. Given any compact set, it must be integral. It need not be integral on the entire space. For example, omega is equal to Rn, and f of x, for example, is equal to x. Then f is in the L1 log of Rn, but integral of mod f for Rn dx is equal to infinity. So it can have infinitely many. It can have the infinite integral, but only on compact subsets. L1 log. Now let us let 1 less than equal to p less than equal to infinity number, define LP of omega. All f belongs to L1 log of omega. So that integral of omega mod f to the power of p dx is finite if p is less than infinity, and essential supremum of mod f is finite if p is equal to infinity. This is standard notation. Let us see. And norm of fp okay. All right. Now with this, what we can do? Now let us start with let us recall some of the properties of the LP spaces. So one more notation I want. The notation for alpha is equal to alpha 1 etc. alpha n, the integers alpha n not equal to 0, alpha a is an integer. Define mod alpha is equal to sigma alpha I, alpha factorial is equal to alpha 1 factorial, so alpha n factorial, and d alpha of u denoted to be equal to d to the power of mod alpha by dx1 to the power of alpha n, dxn to the power of alpha n of u, alpha derivative of u. Okay. And x to the power of alpha is equal to x1 to the power of alpha 1 etc. xn to the power of alpha n. Okay, these are the notations. So now let us look at the LP spaces. Properties of the LP spaces. Of course, first of all, it is a Banach space. Banach space, separable. Banach space. Okay. Now I can just one more. I need some more. Okay. No, this I don't need. Just this. Just recall it. I'll come back to this properties later. Next is convolution. Convolution. What is a convolution? Given any two functions f and g belongs to L1 log, probably, or okay, define f convolution g of x integral over Rn. It may not exist, but just this notation I will make that when it is exists. F of x minus y gy dy. This is called the convolution of two functions f and g. So the entire PDE based on some estimates on this convolution. This is a very, very important object, very important object. Notation. The entire theory depends on the properties of yes. I don't know.
Okay, sorry.
You cannot see?
It depends on my eyes, not on.
Oh, okay. Okay. So let me give some information about this convolution. The most basic theorem is what is known as Engs inequality. Let me state that Engs inequality for the convolution operators. The convolutions Engs inequality. So what it says? So I can define the convolutions for not two functions, for n functions, f1 convolution, f2 convolution, etc. fl. The same, repeat it. Okay. The basic inequality is suppose let this is in Rn. I am looking at in Rn, not in opposite. Let pi 1 less equal to pi less than equal to infinity and 1 less than equal to r less than equal to infinity, such that pi range of p is 1 less than equal to I less than equal to l. There are l numbers, such that pi and r satisfy the following property: summation 1 by pi I is equal to 1 to l minus 1 by r is equal to l minus 1. Suppose pi and r satisfies this property l minus 1. Let fi belongs to lpi of Rn for 1 less than equal to I less than equal to l, then f1 convolution, f2 convolution, etc. fl belongs to lr of Rn. So satisfying the following property: norm of f1 convolution, f2, fr, fl or Rn is the product pi l. So this is the famous Engs inequality. In particular, when say L is equal to 2, this is what you must have learnt in your undergraduate or graduate course, is that norm of if 1 by P1 plus 1 by P2 minus 1 by R is equal to 1, L is equal to 2, then norm of F1 convolution F2 in R is less equal to norm of F1 in P1 to norm of F2 in P2. So this is a famous Engs inequality, and you get here it is now the question is can you reduce, see, can you reduce this is equal to some constant as norm of fp1 into fp2. What is here I have taken that c is equal to 1. Now this constant is a very important constant. Can you reduce 1 to a further down, okay? And in fact it can shown that this constant can be actually computed, and this is by Lieb and Thiering, who showed that he calculated exactly the constant in this Engs inequality, which plays a very important role in physics. I am not going to do anything about it, but let me give the proof of this inequality and reduce this inequality from here. So how does one prove it? So one proves it by the duality argument. So proof is by duality. So look at 1 by r prime plus 1 by r is equal to 1. This is called the conjugate of r. R prime is called the conjugate. So now first prove this inequality for two functions f1 and f2, and then by induction you can prove this inequality. For L is equal to 2 it is. So let alpha plus alpha prime equal to 1, beta plus beta prime is equal to 1 for 0 less than equal to alpha, beta less than equal to 1 be two numbers. So now look at, and h is in any LR function, Rn be any LR function. So now look at f1 convolution f2 on h or Rn. Now before this, okay, this is nothing but by definition Rn, double integral Rn, f1 convolution is equal to f1 of x minus y, f2 of y, g of y, g of x, dy dx. Okay, sorry, h, I made a mistake. This is just the definition. I am just rewriting the definition of convolution. F1 convolution f2 of x, integral f1 of x minus y, f2 of y, dy, multiplied by h of x and integrate it. Okay, now you write it as Rn cross Rn, R to n, call this be R to n. Split this into, okay, modulus of that, modulus of this, therefore it is less than or equal to modulus, everything is modulus. Okay, this one. So assume therefore by taking this, therefore I can assume that f1, f2 are non-negative and h is non-negative. All functions are non-negative functions because to make it life simpler. So you write f1 of x minus y, f2 of y to the power of r. No. I split this into two parts. Split this into two parts. F1 of alpha of x minus y, f1 of alpha prime of x minus y, because alpha plus alpha prime is equal to 1. Similarly, f2 of beta of y, f2 of beta prime of y, again split this into two parts and keep it as h dx dy. Okay. Now, what you do is that apply the LP, you know that, I forgot to mention that, you know that the integral of f1, f2 is equal to integral of norm of f1 in P into norm of f2 in Q, where 1 by P plus 1 by Q is equal to 1. So, this is the standard Holder's inequality. Apply the Holder's inequality for this function, this is for R, this is from R prime and R because we know that they are conjugate to each other. So, therefore, what you get, it is integral R to n. Let us see, I made a mistake somewhere, this is hx by dx. Now, first, okay, let me write down this, just a minute. Okay, this is first integrate with respect to, just a minute, integrate with respect to fine. So apply this. This is less equal to integral of f1 to x minus 2 alpha r f1 to the power of alpha prime r of x minus y double integral r to n raised to the power of 1 by r integral r to n f2 to the power beta r. No, I made a mistake. No, it is a mistake. Sorry. You group the terms like this, not like this. Now this one I write a double integral f1 to the power of alpha of x minus y, f2 to the power beta of y. These two are one term. f2 to the power of alpha prime of x minus y, f2 to the power beta prime of y, h of x, dx dy. So bring these two terms together and these three terms together and apply the Henderson inequality for r prime and r and r prime, and we get what do you get? That's equal to integral of f1 to the power of alpha r prime of x minus y, f2 to the power of beta r prime of y to the power of 1 by r prime integral alpha prime r prime x minus y f1 f2 to the power of beta prime r prime x minus y h of x to the power of r prime dx dy. R prime. Huh? First one should be r. Thank you. First one should be r. So this is the one. This is dx dy. No, this is double integral. Both are double integral. So this is integral of dx dy. Similarly dx dy. Now therefore first integrate over x and change the variable x to x minus y. Therefore the two integrals get separated out. This will get integral over f1 to the power of x to the power of alpha r over Rn dx integral f2 y to the power of beta r dy to the power of 1 by r. So they get in here. F1 of
F2 of y, second integral. Oh, sorry, previous step.
here.
Second product. F2
This
of
is
y.
F2 of y, right? I was wondering. Thank you. Okay. So now first integrate this is fine. Now I want to integrate here. First integrate with respect to deterministic. Okay, here I'll write it as integrate over h of x to the power of r prime times integral f1 to the power alpha prime r prime of x minus y, f2 to the power of beta prime r prime of y dy into dx. This is what I get, raised to the power of 1 by r prime. So here just I want to, where is that? So now let us look at this one. So let us take 1 by s plus 1 by s prime is equal to 1. Now again apply this inequality. Now the integral over Rn f1 of x minus y alpha prime r prime f2 of y beta prime r prime dy. Again apply the Hilbert's inequality Rn f1 of x minus y alpha prime r prime s prime dy to the power of 1 by s prime integral over Rn f2 of y beta prime r prime s dy to the power of 1 by s. Apply this. Apply this. Now this is invariant on this. This is the same thing as integral over Rn f1 to the power of alpha prime r prime s prime dy to the power of 1 by s prime integral over f2 of y to the power of beta prime s prime s to the power of 1 by s. Now substitute this. This is independent of x. I'll get h to the power of r prime. So what I get? I can erase it. What you get is that f1 of x to the power of alpha r, right? So I'll write it alpha r raised to the power of 1 by r f1, then f1 to the power of alpha prime r prime s prime to the power of 1 by s prime r prime. There is an r prime is there, it's there. Then integral over f2 to the power of beta prime r prime 1 by r prime integral f2 to the power of beta prime s prime by s r s prime or 1 by s prime into h to the power of r prime raised to 1 by r. So this is what you finally get. So substituting here, you will get this inequality. This is norm of f1 convolution f2 r to the power of r. No, what I am talking about. Did I correct? R to the power of 4, I made, no, sorry, I made a mistake. This is equal to integral of f1 convolution f2 thing on h. This is what you get. Now I am going to choose this, the alpha and beta. Alpha, beta and s are all my choice. Now choose alpha, beta and s as follows. First of all, I want these to be the same. So I will choose that alpha r is equal to alpha prime r prime s prime is equal to p1. Hello? Oh, yeah, p1. So this I want this to be this one. Beta prime r prime. So these two are the same. Beta prime r prime s, which is equal to p2. Okay. With this choice, if we eliminate alpha beta, I am not going to do this. It is fine. This immediately gives that. What I get? The relation that 1 by p1 plus 1 by p2 minus 1 by r is equal to. If p1, p2 and r satisfies this equation, then you can solve alpha and alpha prime, alpha and beta, just solving it. So once you substitute it, you will get the required inequality, namely and when you substitute all the corresponding things, I am not going to do this. You will get norm of f1 in p1 into p1 into norm of f2 into p2 into norm of h in r prime. This is what you get. Okay, now observe that this is true for all h in r prime. Hence, by duality, it follows that F1 convolution, this is true for all H belongs to LR prime, F1 convolution F2 belongs to LR for law P1. This implies this, and satisfies the norm of So, this is the proof of Engs inequality, famous Engs inequality, which we use it repeatedly in the course of the course, entire course. Okay. And the general formula is by the induction, which the general formula which you wrote is by induction. By induction, you will get norm of F1 convolution etc. Fl in R is equal to product norm of Fi in Pi, where 1 by Pi minus 1 by R is equal to L minus. Use the induction, you will get the result, which I am not going to use it, I just use it for the two variables, two F1 and F2. Okay. This is the first property of the convolution. Then the second property of the convolution is that suppose F is in LP. Okay, let us use the consequence. F is in LP and F1 is in LP and F2 is in L1. So, what is the convolution? F1 convolution F2 is in LP because 1 by P plus 1 minus 1 by R is equal to 1. It implies that R is equal to P. So, this is a second property of a convolution of two functions, an LP function and L1 function is in LP. The third one is that assume that F1 is in LP, now I am going to make F2 my choice. So, what I am going to do is that I am taking F2 to be a very smooth function. So, assume that F2 is in F1 is in LP, F2 is in any compactly supported function in Rn. That is k times continuous differential function such that support of F2 is compact. Then what can you say about F1 convolution F2? Then this implies that this is also in Ck of Rn. Convolution makes the operator smooth. So, how does one prove it? Proof is that F and smooth and d alpha of F1 convolution F2 is same thing as F1 convolution d alpha of F2 for all mod alpha less than or equal to given any integer k, you get that this is the property. So, how does one prove it? It is very simple. F1 convolution F2 of x plus h, say any x plus h minus F1 convolution F2 of x is nothing but F1 of x. Okay, I made one more. Observe that before I introduce that F1 convolution F2 is same thing as F2 convolution F1 by change of variable formula x minus h. So, let us use that here F1 of y, F2 of x plus h minus y minus F2 of x minus y dy. This is what we have. Now, observe that now let us use the mean value theorem. What is the mean value theorem? F2 is differentiable. So, F2 is differentiable means F2 of x plus h minus y minus F2 of x minus y by definition is equal to integral. This is repeatedly I am going to use it, d by dt of F2 of x minus y plus t times h dt. This is just the integration by parts, mean value theorem. This by definition is nothing but integral 0 to 1 F2 of I'll denote the grad f f2 is equal to this vector, or I'll write it as d of f2 df2 by dx1 etc. df2 by dxn. This is the derivative of the gradient of f. Then you'll get d of f2 of x minus y plus d times h, inner product with h dt. This is just the mean value theorem. Substitute here, you will get that I call this I of h, I call this I of h. Therefore, I of h is equal to integral from 0 to 1 f1 of y, this is I'll get it integral over Rn f1 of y df2 of x minus y plus dh h dy dt. So, this gives the result whatever you want. Now, let h tends to 0, you will get the, you can erase it. So, what you get? Therefore, you will get f1 convolution f2. Now, v is any vector, or v, let now I take h to be equal to some ei is the ei times h, h is replaced by ei times h is a real number, and ei is the vector 0 0 0, 1 on the ith place, the rest is 0. Therefore, I am taking the derivative of this. Therefore, d by dxi of f1 convolution f2 of x is same thing as h tends to 0 f1 convolution f2 of x plus ei times h minus f1 convolution f2 of, I made a mistake, yeah, no, I have not made any mistake, convolution f2 by h. This you can see that by passing to the limit and use the dominated convergence theorem, you show that this is same thing as integral over Rn f1 of y df2 dx of x minus y. So, by the, this is same thing as f1 convolution df2 by dy. This is y I, this is y I, right? Y I. So, that proves that when alpha is equal to 1, repeated this process. Therefore, all the derivatives you can take it on f2. Therefore, this forms that this is a CK function. Okay, fourth one, I would like to, third or fourth one. Suppose f1 and f2 have compact support. Assume that f1 and f2 have compact support of f1 and support of f2 is compact. I don't need it, but just I am telling compact. Then f1 convolution f2 has compact support. And where does the support contains? Then support of f1 convolution f2 is contained in support of f1 as support of f2. So, this is another important property which I need it. So, what is given? Support of f1 is contained in k1, let us say k1, support of f2 is contained in k2. That is what I mean is that f1 is equal to 0 for all x does not belong to k1, f2 of x is equal to 0 for all x does not belong to k2, right. Now, look at f1 convolution f2 of x is nothing but integral over Rn f1 of x minus y, f2 of y dy. Then since support of f2 is contained in k2, therefore this integral is only over k2 because y is there, outside y it is 0. Now if x minus y does not belong to k1, if x minus y does not belong to k1, then this is also 0. Implies that f1 of x minus y is equal to 0. So this is equivalent to saying that x does not belong to y plus k1. This implies that therefore if x does not belong to, for all y, this is for all y, k2 plus k1, then f of x minus y is equal to 0 for all y belongs to k2. So that means that this is equal to 0 if x does not belong to k1 plus k2. So if they are compact supported, then the support is also compact because k1 plus k2 is compact. Therefore, the convolution of two compactly supported functions is still compactly supported. This is the property 4. Okay. Okay. Maybe I need one more property before going to the I need the mollifying sequence, mollifiers. No, maybe before that I may need something. Yeah, mollifiers is good. Let us start with the yes. Okay. So let us go to the mollifiers. What is a mollifier? Now you know that okay. Now let rho be a symmetric function with compact support in Rn, having the following property. Take any rho which is compactly supported function. You know that compactly supported. I hope everybody knows. MSc students know this. Huh? Okay, good. Let rho be a symmetric function with compact support, having the following properties. Such that rho satisfies the following property: 1, rho is a non-negative function. 2, integral over Rn rho x dx equal to 1. Take such a function rho. Then for every epsilon positive, define rho epsilon of x is equal to 1 by epsilon to the power of n rho of x by epsilon. Okay. Then this family of functions rho epsilon is called mollifiers. So what are the properties of the mollifiers? Let us recall the properties of the mollifiers. So properties of the mollifiers. 1. Suppose support of rho is contained in the ball of radius 0, 1. Now that is rho x is equal to 0. That is rho x is equal to 0 for all mod x greater than 1. Now look at rho epsilon of x. Rho epsilon of x is same thing as 1 by epsilon to power of n. Therefore, rho of x by epsilon. This implies that this is equal to 0 for all mod x by epsilon is greater than 1. This is equivalent to saying that rho epsilon of x equal to 0 if mod x is greater than epsilon. This implies that support of rho epsilon is contained in the ball of radius. So it strings, okay, something like this. If rho is like this, suppose I got rho is something like this, rho epsilon is something like this. This is 1, 1, this is minus epsilon and plus epsilon. This is rho epsilon, this is rho. Okay. Okay, this is first property. Second property is that what happens to this rho epsilon of x for Rn? This is named same thing as epsilon to power of n rho of x by epsilon dx. Now put y is equal to x by epsilon, then dy is equal to dx by epsilon to power of n. This epsilon to power of n and dx makes it to be equal to rho of y dy for Rn. By the property this property, this is equal to 1. Therefore, for every epsilon the mass is the same. So what happens is that I am taking a function rho, something like this, say, says that the area under this integral is equal to 1. Then for any epsilon small, it goes to like this, minus epsilon plus, still the area remains the same.
Therefore,
so basically it is called, physicists called rho epsilon as a Dirac mass, but mathematicians don't say that it is a Dirac mass, it goes as epsilon tends to 0, it goes to Dirac mass, which I am going to tell what it is about in a few minutes. So rho epsilon is called a mollifier. Okay. Why these mollifiers came into picture? I'll give a small history of this problem. The history of the problem is the following. So you have, let us say, so you have the functions, basically, take the real number system. Real number system consists of rational numbers and real numbers, irrational numbers. And now if you, irrational numbers, basically you can define an irrational number, that is what Dedekind did in his famous Dedekind's cut. But capturing an irrational number is impossible. You cannot write down because the decimal expansion is there and it is infinite. You cannot. Therefore, even though, but irrational numbers are very, very important for the completeness property of the real number system to work with them in mathematics in full generality. But if really want to compute anything, you cannot compute an irrational number. What you can compute is an approximation. That approximation comes from the rational numbers. So what really matters, you work. In reality, you work only with rational numbers, but you don't with the irrational numbers. But irrational numbers are very important if you want to prove some theorems. Okay. Now from real number system, if you go to, once you have real number system, you have got the concept of functions on the real number system. So functions, that is, now you are looking at the bigger space of functions. In that functions, again you could take the subcategory of functions. There are all functions which are continuous functions. Okay. So and you have got on the real number system, instead of entire R, let's fix it the interval 0, 1. 0, 1. And look at all continuous functions in the closed interval 0, 1. All f from, so this is denoted by continuous, say C0 of 0, 1. These are all continuous functions in 0, 1. It is a huge class of functions. Now like R is there, Q is contained in this. This is computable and which is dense. Any number can be approximated to Q. So you know, given any number, I know that there exists a number here which is close to that. That is good enough for me. Now again the same concept you would like to know that if we have got a space of continuous functions, given a continuous function, I must get another function which is computable. Okay. So we know that what are all the computable functions here. The computable functions, you know, by hand you can calculate it, the constant functions. Then x square, or any polynomial in x. So polynomials are the polynomials with real coefficients. Again replaced by real quotient by the rational numbers. Therefore, you can polynomials with rational numbers are computable. You can calculate it. Okay. So that means this polynomials, they call this C of x. The polynomials, class of polynomials is the one which sits in the so this is the C of x, I call this polynomial in x, which sits in the all continuous functions in 0, 1. These are all computable functions. Given a function, I don't know how to compute it. Therefore, now natural question you would like to ask is there a corresponding result like in real number system in this space of continuous functions? That is, in a real number system, you know that the space of rationals is a dense subset. Therefore, you would like to ask the same question, that whether the space of polynomials is dense in
C of 0, 1.
Is it clear? So this is the corresponding question we are looking at it. This is Everywhere we are doing the same thing. This philosophy remains the same throughout my lecture. That is, I define some space which is very complicated, but I don't know how to deal with it. But I try to find some subspace which is computable and which is dense. This is the philosophy of entire mathematics. Okay, wherever you do, whatever research you do. So this is the basic theorem which you want to know. The basic theorem, basic result which I am looking for is the corresponding dedication theorem here, whether it holds here. That is, the space of polynomials, whether it is dense in space of continuous function. That is, given any continuous function, can I find a polynomial which is which can be approximated by a polynomial? Is it clear? So this is the proof of theorem which is due to Weierstrass, a famous theorem due to Strauss. I hope you have learned this. Weierstrass theorem says that polynomials are dense in space of continuous functions with the what is the norm? Sup norm with respect to this norm. X belongs to 0, 1. I call this the norm of f in C0 norm. That is, given any continuous function, I can find a polynomial such that I can get a sequence of polynomials such that sequence of polynomials converges f in this sup norm. So this is the famous Weierstrass theorem. So how does Weierstrass prove it? Before going to this, I think most of you have learnt in your MSc. Have they do they learn? Okay. What is the proof you learn? The proof is the what is it? Bernstein polynomials. Okay. So Bernstein polynomial, just a diversion. I want to give some history of this because this plays a very important. What is a Bernstein polynomial? Bernstein polynomial, given a continuous function f, the closed interval 0, 1. Okay. Something like this. 0, 1. So what is a Bernstein polynomial? Bernstein polynomial follows from the simple identity. What is the identity? The identity is nothing but what is identity? Identity is equal to 1 plus x minus x, right? So I will write a 1 is equal to 1 to the power of n, 1 plus x to the power of n. Let me write 1 minus x plus x to the power of n for x belongs to 0, 1. This is a positive number. Now apply the binomial theorem. You will get NCR x to the power of r 1 minus x to the power n minus r. This is a famous, just one identity. It comes from the binomial theorem. So this is identity 0 to n. Now what Bernstein did? Do you remember how the Bernstein polynomials are constructed? Given a continuous function, you divide this interval into n parts, 1 by n, 2 by n, etc., n minus 1 by n, n by n, right, is something like this. This is my f. Take the values f at the point r by n, r ranges from 0 less than equal to r less than equal to n. Take this one and insert here f of r by n, and this is the Bernstein polynomial. Is it right? So this is the Bernstein polynomial. Just introduce r by n at this one and show that as n tends to infinity, sorry, x by n. What I am talking about? X by r. No, x. R by n is correct. Yeah, r is the right. You are right, sir. R by n. Now this is a polynomial. So what it says that suppose you are given a function and r by n is a rational number. Evaluate this function at the rational number r by n. You get the values and substitute in this identity as the coefficients of this one. You will get a polynomial. And Bernstein showed that as n tends to a number of divisions is finer and finer, this converges to the given function in the C0 topology. This is a famous Bernstein theorem. Now the question is, this is not the proof which Weierstrass gave. Okay, this is where I wanted to tell you this. What is the Weierstrass proof? Weierstrass proved in a entirely different way. What he proved is the following thing. I think because this Weierstrass theorem has two directions. One is the original proof, this is Weierstrass theorem, original proof. Another is the Bernstein polynomial proof. Okay. So two have two different directions it goes. So what I am going to talk about the original proof, where does it lead? The original proof, what he does is that, okay, let me use this. This is more, both are appropriate for this course because most of the times you are talking about the stochastic process, and both are very, very important from the stochastic point of view. So let me first start with the original proof. What original proof says that what he does is that he solves the heat equation. So he solves the heat equation du by dt is equal to Laplace u double prime d square u by dx square in the interval say minus plus infinity cross r 0 infinity with the initial condition u of x0 is equal to u naught of x, and using the Fourier transform you can solve this equation as the u of xt is equal to 2 pi t to the power of n by 2 integral e to the power of minus x minus y the whole square by 4t u naught of y dy. This is the solution. You can write down explicitly the solution of this equation, and this is a solution. It can be shown. Now, if you look at this one, look at my phi of x. Phi of x is equal to 1 by 2. Sorry, it is n by half. 2 pi to the power of half e to the power of minus mod x square by 4. This is my function phi of x. So now I am taking epsilon is equal to 1 by root t. Take epsilon is equal to 1 by root t. This is the definition I am taking it. T is a number, positive number. Take epsilon is equal to. Now I am going to define my modification. Now my modification is defined like this with respect to not rho, with respect to this function. This is called the Gaussian. Take this Gaussian. Take the modification. Put epsilon is equal to 1 by root t. So what you get? When epsilon is equal to 1 by root t, I will write 1 by. Sorry, epsilon is equal to root t, epsilon is equal to root t. So I will get phi of root t of x by definition is equal to 1 by 2 pi 2 square root of 2 pi. There is n is equal to 1, here n is equal to 1 because one dimension I am looking at it, 1 by epsilon, 1 by root t, this is what you get, is times phi of x by root t. This is same thing as 1 by square root of 2 pi t e to the power of x square by 4t. This is what you get. And if you look at this one, this is precisely equal to phi of root t convolution of u naught of x. The convolution comes automatically in this setup. Therefore, a solution to the heat equation is given by the convolution with respect to the Gaussian of root t. And you know that according to this one, u of xt goes to u naught of x as t tends to 0 because u at t is equal to 0 is equal to u naught of x. This converges. Now this is a convolution with respect to this. Now what happens? Assume that u naught has compact support. U naught is a continuous function with compact support in R. Okay? So, is it clear? So now once you have this, now Weierstrass idea comes. What you do? E to the power of mod x minus y whole square, you expand it terms of the Taylor series. It has a power series expansion. You truncate it and arrange the terms. Then this becomes a polynomial in x, and that polynomial converges to the function phi of u naught. So this is the original proof of Weierstrass. He uses the convolution and the Gaussian. This is where the Gaussian come into picture. So there is one line of thought. There is the convolution. So later on what Friedrichs, what he used is that he made use of this convolution. So he thought that okay, let us this is the Gaussian, you get it. It is a rapidly decreasing function. Instead of this, you take the functions with compact support and define the modifying sequence like this, and see what these are the properties it satisfies. What are the properties? And this is really the fundamental concept which is used in the theory of sublaw spaces and theory of distributions. Okay, this is one line of thought from the Weierstrass approximation theorem. There is another line of thought, that is Bernstein polynomial. Weierstrass Bernstein polynomial gives a polynomial approximation. Now Stone came, afterwards the Stone, he came and generalized this to what is known as Stone-Weierstrass theorem. He is completely in generality, okay, in algebra. Now you take an algebra which satisfies certain properties, then it is dense. So once this Stone proved that what is known as, have you heard about Stone-Weierstrass theorem? Huh? Yeah, how many of you don't know? Okay, Stone-Weierstrass theorem says that if you look at its P of x, the polynomial is contained in C of x, okay, C of 0, 1. Just look at it. Now, what are the properties P of x satisfies? Okay, properties of P of x is P of x is an algebra. It is a vector space and two functions can be multiplied, still it is a polynomial, and given any 2 points you can always separate it by a polynomial. So it is an algebra satisfying all these properties, namely it separates the points and it is one constant function 1 belongs to this. So once you have these two things, now can you replace this by any other thing in algebra A which satisfies the same properties? In algebra, it is an algebra, consists of constant functions, and given any 2 points, there exists a function in the algebra which separates these 2 points. Suppose you put these 2 properties. Now ask the same question. Does it imply that the closure, A closure, is equal to C of 0, 1? And the Stone-Weierstrass theorem precisely says that the closure of this algebra is precisely equal to C of 0, 1. So this is the Stone-Weierstrass theorem. Once Stone-Weierstrass theorem is proved, then we get a very famous result due to Kolmogorov. It is in Kolmogorov, which you are going to learn in your stochastic process. The famous theorem, which is his thesis, the consistency theorem, construction of probabilities on infinite product. That the proof relies on the Stone-Weierstrass theorem. Okay, you need some density arguments to construct it. Once you have that, then you will get Brownian motion and blah 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 everything comes, which you are going to learn this. So there are 2 things. This is such a fundamental theorem of the concept of the density. You lead to 2 important. This gives the PDE. This gives the stochastic PDE and the stochastic calculus, etc. Okay. So therefore, modifiers are the very important concepts. Okay, with this story, let me come back to the properties of, let me go back to the properties of convolution. Okay. Unfortunately, this proof we never give, nobody gives in the MSc course, this convolution, okay. As far as I know, at least in the Indian universities. Okay. So where we are, we have the convolution. So we have the modifiers and convolution. So I use this modifiers and convolution. So let me first prove the Weierstrass theorem here. Something like this. Weierstrass theorem. What is the proposition? Let f be a continuous function with compact. This is a compact support continuous function now Rn. F is a continuous function with support of k is compact. Now then rho epsilon convolution f is a symmetry function with compact support in Rn for every epsilon positive. 1, 2, limit epsilon tends to 0, rho epsilon convolution f is equal to f in C0 topology, in supremum topology. So this is what I am going to say. It is a Weierstrass theorem. I am going to prove the Weierstrass theorem. Weierstrass proved it for the Gaussian. Here I am going to prove it for this one. So it is just a consequence of clearly one is obvious proof. Support of f is compact. Support of rho epsilon is compact because support of rho epsilon is contained in the ball of radius epsilon. Assume that. Therefore, support of rho epsilon convolution f is contained in. Therefore, support of rho epsilon convolution f. Basically, I am assuming that always that support of f is contained in ball of radius 0, 1. Okay, just is contained in support of f, the support of rho epsilon, which is equal to support of f plus ball of radius 0 epsilon. So we call this be k plus ball of radius 0 epsilon. which is equal to k epsilon. Denote this k epsilon to be the k plus ball of radius epsilon. Therefore, support of rho epsilon is contained in, it is certainly contained in k plus b of 0, 1 for any epsilon less than equal to 1. So, it is contained uniformly and compactly supported. They are compactly supported functions. Now, let us look at it rho epsilon of x, sorry, what is rho epsilon convolution f of x minus f of x. Okay. This by definition is equal to f of x, f of y, rho epsilon of x minus y dy minus integral of f of y. Okay, before that I want one small formula. What is the rho epsilon of convolution f of x? The same thing as 1 by epsilon to the power of n f of y rho epsilon of x minus y, sorry, rho epsilon of x minus y by epsilon dy. This is the definition. Put x minus y by epsilon is equal to z. Then by change of variable formula, you will get that f of x minus epsilon y rho of y dy, rho of z dy. Just the change of variable formula, you will get this one. I can take either here this or here. I work with both the things. Therefore, I will write it as this is nothing but f of y, sorry, f of y. Now, I know that f of y I can write it as rho epsilon of x minus y dy, because this is always is equal to 1. That is what the property of the mollifying sequence. For any epsilon, this is true. Therefore, I can club both the things. You will get that f of y minus f of x rho epsilon of x minus y dy. This by definition, now change the variable, you will get f of x minus epsilon of y minus f of x rho y dy. Okay. Now, support is contained in K1 because for any epsilon less than equal to 1, the support is contained in ball of radius 1. Ball of radius 1. Now, f is a continuous function, therefore, it is uniformly continuous. Therefore, this converges to 0 as epsilon tends to 0. Therefore, by dominated convergence theorem, this converges to 0 uniformly in X. So, it is used the uniform convergence on a compact subset, you will get the result. Therefore, as epsilon tends to 0, using the dominated convergence theorem, you will get that this converges to 0 because I can take the positive limit as epsilon tends to 0, I will get fx minus fx which is equal to 0. So, this is the Weierstrass theorem in simplified Weierstrass theorem. Okay. So, one more thing I wanted to, again in the same thing, as a corollary to this, suppose f is equal to k times continuous differential function in Rn, then look at rho epsilon convolution f converges to f in CK topology. That is what is CK topology? That is supremum of x belongs to Rn modulus of x minus rho epsilon convolution f of x, write it as summation epsilon, I call it epsilon. This is for all model. So what we have proved here is that if f is a continuous function, then the rho epsilon convolution f converges to f in a C0 topology. Supreme norm converges to 0, right? That is what we have proved. So what we have proved? Earlier we have proved that supremum of modulus of f of x minus rho epsilon convolution f of x for x belongs to Rn, this equal to 0, limit as epsilon tends to 0. It follows from this identity, uniform, okay, because rho f is compactly supported. So this is, we have proved this one, that is when k is equal to 0 we have proved it. Now for k greater than or equal to 1, all you have to observe is that d alpha of fx, d alpha of rho epsilon convolution f, we already proved that. Same thing as rho epsilon convolution d alpha. We already proved that convolution satisfies, when I differentiate it, I can take the derivative inside the convolution. So once you use this and use this, now replace f by d alpha of this, and that gives the result. Sum it over for all k, you will get this result. So therefore, what it says is that symmetry functions with compact support, is dense in symmetry functions with the k times differential functions for any k. So this is another important density theorem which we are going to use it. Okay. Now I think I got 2 minutes time. Maybe I can stop at this is the time to stop at. So I am going to stop this. So these are all the preliminaries that I required before introducing the concept of sublaw spaces. What I am going to do in the next class is that I introduce the concept of sublaw spaces and then prove the properties whatever I stated. Density, first thing is the density theorems, that is what I said. That is my philosophy. Philosophy is that give whatever I define, I must get a computable space. So basically therefore I have to first spend time on the computable spaces. Once I get the computable spaces, therefore then you can throw away your original space and whatever properties you want to require, you just work with the computable spaces and then say that pass by density argument it is true for any. This is the general nonsense. Okay, this is what to do. Once you define this, then we go to the Fourier transforms and PD. Okay, so this is what I want to do. Any questions? Okay, good. Okay, all these things are in